So begin with process synchronization. In my earlier video, I have introduced to you what is synchronization, what is the need for synchronization, and what happens if processes are not synchronized. Now, before I take on the discussion further, I would summarizingly talk about the same thing again. So, processes, when they are communicating with each other, must be synchronized. If they are not synchronized, then perhaps it will lead to the problems. If you remember, I told it like inconsistency. I'm writing in short, inconsistency, or if not, it may even lead to data loss of data. And finally, the third thing that can happen is deadlocks. So lack of synchronization may perhaps lead to the following problems: inconsistency, data loss, deadlocks. All these three I have explained to you. Refer to my previous slides for just in case if you don't remember. So therefore, in this regard, we consider this problem to be named as what is called critical section problem, CS, critical section. What is critical section? Critical section is that part of the program where shared resources are accessed. I have explained in my previous slide. So therefore, the non-critical section is that part of the program where we do not access shared resource, and critical section is that part of the program where we access shared resource. So this is the model or the architecture I said. We may have multiple processes, P1, P2, P3, all want to enter critical section. So if you allow all of them to enter critical section, either I may get the problem of inconsistency, data loss, or deadlock. So therefore, we want only one process at a time to use critical section. This is what is called the requirement of critical section problem, which is to be implemented by whom? Which is to be implemented by a synchronization mechanism. I write in short SM, synchronization mechanism, synchronization tool, synchronization algorithm, either way you call it. Okay. So this synchronization mechanism, you have to imagine, is like your security guard protecting critical section. Security guard, GUARD. Okay, security tool. So this synchronization mechanism has two parts: entry section and exit section. Entry will allow only one process to enter. I have put one line here. Only one process should enter. This is like security. It is allowing only one by one, security guard. Then the process coming out from critical section will execute the exit section to inform the other processes that I have come out. One of you can join. Like if you want me to explain, it goes like this. And all three want to enter. They will inform the entry section security guard. Then P1 is allowed to enter first, let us say. Then what will happen? P2 and P3 will wait till P1 completes critical section. Okay. Once P1 complete executing the critical section code, it will come out and execute exit section, which will send a signal to P2 and P3. P2 and P3 are waiting, so it will get a signal. They're saying that, okay, critical section has become free. P1 say, I'm going out. Then P2 or P3, any one of them will enter critical section. Okay. Then P2 comes out executing its part. Then it will signal P3. Then P3 will enter. So sequential we allow one by one. That is the job of this synchronization mechanism. So this principle of allowing only one process to enter critical section is called mutual exclusion. Sometime I write in short mutual exclusion, ME. Okay. Principle of mutual exclusion, which is one of the requirement to be satisfied, is nothing but allowing only one process to use critical section at a time. Then second requirement to be fulfilled is called progress. What is progress? If somebody is not interested in critical section, imagine P1 is not interested in critical section, then it has got no right to block P2 and P3, no right to tell P2 or P3 that you enter, you don't enter. It is not supposed to interfere. Okay, that is called progress. So if somebody is not interested, let it not disturb others who are not interested, P2 and P3 are interested, let them go. P1 should not prevent it. That is progress. Then finally, what is bounded waiting? These definitions I also ask you to see from the slide which I am going to share. Okay, right. Bounded waiting means no process has to wait forever to enter its critical section. That means if 3 want to enter, you allow P1 first. P2 and P3 are waiting. Then P1 comes out and want to enter again. Again, if you allow P1, P2 and P3 will starve. So if you keep on allow only one process or a set of processes and ignoring the other process will keep on waiting and will be subjected to suffer from the problem of starvation. So to avoid that, we say bounded waiting condition should be satisfied. So if any mechanism satisfy these three requirements, then we say it is one of the correct mechanisms. So this could be a simple 3-mark question for your exam, please. They may ask, what is synchronization mechanism? 2 marks. What are the requirements of synchronization mechanism? Explain. So whatever I explained just now, if you write, you will get full 100% marks. Okay. Now we'll continue. I told in my last slide, synchronization mechanisms are basically three of them we need to discuss here as part of your syllabus. One is called Peterson solution. Peterson algorithm or Peterson solution. The other is called hardware synchronization. And the last one we are going to discuss is called semaphore. So these are the three things you can expect in the exam on any in any fashion. Okay. So again, I say, have a look at it. Three type: Peterson mechanism, hardware synchronization, semaphore. So any of these you can expect a 10-mark question in the exam. So let's continue with the individual discussion of each of them, how that is going to be solving the problem of critical section. Okay, so let's take one by one. First, I'm going to begin with Peterson algorithm. So I'll write the Peterson algorithm, then we'll understand. Okay, right. So this is the Peterson algorithm. You can even see this algorithm from the slide. It is present, it is given in the textbook with a slight variation. I am improvising the code. I am adding few more statements for your better understanding. So it looks slightly different from the one which is given in the textbook. So either you can follow the textbook one or this one. Okay, so let's see. So here are the data structures of Peterson algorithm. What are the data structures? Let us review one by one. Define n. This n indicates the number of processes. So this is defined for only two processes. You may name the processes like, you may name it, let's remove this line. Okay. So let me put it. Okay. So these are the two processes. Maybe you can name the processes as Pi, Pj. Two distinct. I is not equal to j. P0, P1, P1, P2, P3, P4, something like that, I and j. Now for each process we are maintaining a flag. Flag is going to indicate what is the current interest of the process. I mean whether the process is interested or not interested. So please understand the meaning of the data structure. If you follow my instructions, if you follow the explanation here, it becomes easy for you. Otherwise, if you try to read it from textbook, it becomes difficult. So therefore, I am repeatedly telling you, follow my explanation so that you can easily understand from the textbook or the slide. So for every process I and j, we are going to maintain a flag which is going to indicate what is the current interest of the process. I mean, is the process interested in critical section or not interested? So if the process is interested in critical section, then flag will be true. If the process is not interested in critical section, its flag value will be false. Initially, both the processes are not interested, so therefore the value of the flag of both is false. So flag of n, flag of two processes is false. Then we also have a variable called turn. Turn is going to indicate which process turn is it to access critical section. Okay. Suppose what happens is, if both processes are interested in entering critical section, then turn will play the role of a toss. Just we raise a toss, we make a toss. Whoever win the toss will go to critical section. Whoever will lose the toss will wait. Okay. So if only one process is interested in critical section, other is not interested, then there is no meaning of turn. There is no much definition of turn, or there is no much role of turn. So turn will come into picture only when both the processes are interested in critical section. So if only one is interested, other is not interested, there is no much role of turn. If both are interested, then both of them will make their flag value to true. Then they will make a toss like turn. I will show you how turn will play the role. And then whichever sets the turn, whichever wins the turn will enter critical section and other will wait. Okay. So with this explanation, let's review the understanding of our algorithm of Peterson. So kindly remember, this is defined for only two processes. I am naming the processes as I and j. I and j are distinct, mean the value of I is not equal to j. Say for example, if I is 0, then j will be 1, and if I is 1, j will be 0. This is the meaning of the code. Okay. So I'm naming the processes as 0 and 1. So let's see. So suppose if the executing process is I, j will be opposite to it, not of I. If I is 0, j will be 1. If I is 1, j will be 0. Got it? This is the meaning of the process. Now the processes will be running in an infinite loop. What is the first thing? First thing is non-critical section. That is some part where the process is not interested in entering critical section. Then what is the second line? Flag of I is equal to true. The process who is interested in critical section will change its value of flag, will make its flag value from false to true, saying that I am interested. So let's say process I is interested in critical section. Then in that case, the other process concurrently, suppose if I is 0, then flag of 0 become true. Later I become 1. Process 1 also say I am also interested. Both are concurrent process. So this fellow will also say I am interested. So both are interested, or only one is interested, as the case may be. Then if the process say that, okay, bhai, you set your turn. So every process will set the value of turn to myself. So process P0 will say it is my turn. P1 will say it is my turn. So turn is only one global variable. Look here, turn is only one global variable. It can take either 0 or 1. So suppose if P0 set turn to 0, so turn becomes 0. Then P1 updates, so turn become 1. Meaning whichever process sets turn last, okay, will be the final value of turn. So if 0 set first, turn becomes 0. Then if 1 set the turn, then turn become 1. Whichever process update turn last, that will be the final value of turn. So turn is equal to I. Then after that, the process will check whether I am the first one to update turn or am I the last one to update turn. Am I the first one or am I the last one? So here we test. So this is a very crucial loop. I am highlighting it for your understanding. So here process will either proceed to critical section, will win the critical section, or will wait. So process I is 0, so j will be 1. So if flag of j is true, other fellow is also interested. Please understand, if this is not true, then I will this become false. Okay, so false ANDed with anything will be false, so this fellow will enter critical section. Problem will arise when this is also true, I is true, j is also true. Why I is true? Here it is true. Flag of I is true and j is also true, both are true. Then this fellow will say, am I the first one to update turn? Turn is equal to I. Am I the first? Am I the last one to update turn? Not first. Am I the last one? So turn is equal to I. Then I will wait. Process I will wait. Otherwise, if I am not the one, the value of turn is not equal to my ID. So j has updated last. So therefore, I will enter critical section. So again, I repeat, process I, who is right now executing, will set its turn flag value to true and will update turn. Then it will check whether what is the state of other process. If other fellow is not interested, directly jump into critical section. If other fellow is also interested, then it will test turn is equal to I. Am I the last one to update turn or not? If I am the last one to update turn, then I will wait. Otherwise, I will go. Then coming out from critical section, very simply, I will set the value of flag to false, saying that my job is done. I am no more interested. I am going back. And this will continue like this. So this is how we can guarantee all the requirements. So as you would see from the code, it will guarantee mutual exclusion. I am writing in short. It will guarantee progress, and it will also guarantee bounded waiting. All three requirements are fulfilled with this. Just now I proved mutual exclusion is guaranteed. Progress is very simple. If I said if flag of j is false, other fellow is not interested, so it will never prevent the interested one to enter critical section. And by making a sequential sequential trace, you can prove that if process I enter first, j will not be allowed, and process I coming out and want to enter, it will never be allowed. So therefore it guarantee bounded waiting. This is one of the correct mechanism for solving the problem of critical section, meeting all the three requirements. Okay, so in the exam you can straight away expect a 5 mark or 10 mark question directly on this. So I want everybody to please understand the code. If they ask to explain Peterson algorithm, this is what you need to write, this is what you need to write the algorithm and explain as I have explained. You will straight away get 5 marks. I hope it is clear. Okay, so do read it. There is some slight change in the textbook version. In the textbook they write turn equal to j. If you write turn equal to j, here also you should write turn equal to j. If you write turn equal to I, here also you should write turn equal to I. So either way you can follow the convention of textbook or the one which I am explaining here. Both of them are equally correct and both of them are valid. I would advise you can follow, because most of the examiners follow textbook convention. You follow the textbook convention, but my explanation you follow here to understand and reproduce in the exam. Okay, all right.